uniformly continuous, the continuity here is very similar as to the continuity of a function in a specific point, but with the difference now that the value of delta must be the same for all the elements, for all the numbers inside of this set. Okay, so the definition is said a function defined in a domain D, which could be a subset of the real numbers, we say that is uniformly continuous on D if for every epsilon, any epsilon that you want, greater than 0, there will be a delta such that we can make the function for every x and y inside of this epsilon here, the evaluation will be below the epsilon whenever these x and y are, the distance between them are below delta. Okay. One example that we have here is, let's say, a linear function f of x equal to 2x. So if we give any epsilon greater than 0, we need to make this evaluation super small such that they will be less than epsilon by making x sufficiently close to y, right? So in this case, if we need to make this very small, we can put the evaluations, okay, x to the x, and here we have 2 in both sides, so we can move 2 outside and do the factorization. And we will have this part is one of the part that we want to make it super small, right? Like the definition. We want this part to be less than epsilon. So then what? If we let this epsilon to be, this delta to be epsilon over 2, right? This 2 is because we have the 2 here, right? Then whenever this is super small, is less than delta, we have also that the evaluation of these both points is below, right, that the epsilon, which is equal to delta, to epsilon, okay? Then f is uniformly continuous. See this this part, of course delta depends of epsilon. However, epsilon will be multiplied by a constant number. Basically, it is linearly related to epsilon, to delta. We have to be clear with that. Now, uniformly continuous, this is the definition, right? If we have the function to be uniformly continuous on delta, if for every epsilon greater than 0 there exists a delta greater than 0 such that this distance is super small, less than delta, right? Then it implies that the evaluation of the function will be less than epsilon. If we do the negation of this, the negation basically will be, okay, f is not uniformly continuous, right, on the domain D if, right, there exists an epsilon greater than 0 such that for all, remember that here it was there exists, right? Now we change it for all deltas greater than 0, there exists an x and y into D such that the distance between them is less than delta and the evaluation of the function is greater or equal to epsilon, right? So if we write this in uniformly continuous definition in formal way, we will have that here what I said here is the same, right? Whenever we have the for all epsilon greater than 0, I say here exists an epsilon greater than 0, exists delta greater than 0, I will say the negation is for all deltas greater than 0, and so on. See that this implication change, and because it's a negation, we move the or to and negated everything else, right? So we will have, instead of say that whenever the values from x and y are less than delta, then implies that the distance between the evaluations is less than the epsilon. We said here that okay, we will have this one, will keep it as it is, and we will have the evaluation, the distance between the 2 points in the evaluation is greater than or equal to epsilon. So why we should know the negation? The negation is useful sometimes. For example, whenever we have, let's say, x to the power 2, right? This function. In this function, we will have that if we get the evaluation, we will have the difference of the squares, and if we do the factorization, we will have this. We already have this term, which is what we want to be less than delta. However, we don't know exactly how it will be the other one. This one is changing, right? I cannot put this term inside of as a part of the definition of delta, because it's changing, it's not constant, and we are looking for a constant number to be uniform continuous, right? For example, in order to keep, let's say I said epsilon is, let's say, equal to 1, and we have the neighborhood here, I can have a delta 1 here that is bigger than delta 2, that is for the same epsilon equal to 1, but in another point of x2. What happened here? If I said that if we are going to use epsilon 1, delta 1 for all the points here, it will not work, because the delta 1 will be here, and some of these points will be outside, right, of this epsilon. The idea, it will be ideal if we use the minimum delta in this case. But what is the minimum delta if this function is in a domain of the real total real number? We will not have a minimum. We will not have a specific delta that will cover for every single point, right? So making this more formal, let's suppose that the epsilon is 1. So then we need to show that given any delta greater than 0, there exists 2 points x and y inside of the real set, such that what I said, the distance between these two numbers is less than delta, and the distance between the evaluation is greater than 1. We are using here the definition of the negation. We are trying to prove that this is not uniformly continuous. So in this case, we have, for any x, we let the y to be this number. This is basically, we will have the same x plus the delta over 2, right? This number, why we have this number, what we are trying to show is a case that this will happen, that if I take this delta in here, right, this delta in here, I will have a point that is outside of the range that I want, right? So we can say that 1 is less than this, and this is equal to whatever we have in this side that we don't know, multiply it by the delta over 2 that we say that it will be greater than, right? That is because we use this. If we substitute it here, we will have, right, this one. We have x minus x plus this one, right? So this x will go away, and we will keep only this one, this part, right? Then basically what we said is that x will be 1 over delta if we do the substitution in the other side, right? Then what? we already have the epsilon 1. We are given that the delta is greater than 0. We know that x is 1 over delta. And y is 1 over delta minus delta over 2, right? Which we said before, right? Then if we do this, basically we have that delta over 2 is less than delta. Until here everything is okay, but the evaluation of these two functions, basically if we change this variable by the equivalence in delta functions, we will have this, right? So we will have 2 of this plus 1 of this multiplied by delta over 2, which is greater than what we have before, which is 1, right? Therefore, it is not uniformly continuous on R. However, we have to see here, if we have a closed interval, basically a compact set in the real line, then we know what will be the minimum delta that will make these functions to be to make it work, right? So if I have this is the part that we didn't know before, right? We were looking for this part that we don't know, and this part that is the part that we are trying to make it small. So for this part that we don't know basically how much it will be, we can say it as a maximum it will be less or equal to x plus y, right? X plus y are both numbers of this interval d. So the maximum one that we can have, it will be 5, right? So if I have 5 plus 5, I will have 10. Then if I take a delta equal to epsilon over 10, then I can guarantee that it will work for all the epsilons that you want to have, right? So we do exactly the same thing, and I will say that this part is less than or equal to 10 multiplied by this term, which is the minimum distance that we have to find, which is less than 10 over delta, which is equal to epsilon. Then the quadratic function is actually uniformly continuous only when it is taken inside of a compact set. So what we need to understand about the uniformly continuous is that the relationship between delta and epsilon have to be a constant number. The function have to be bounded by a linear function. If we have an upper bounded linear function on this function, we can make it for all the numbers inside of the real numbers. If that is not the case, we need to have a closed interval. Okay.